Hello friends, welcome to our channel, Gajpal Learning. In this video we are going to study about the topic, Complexometric Titration, its types, and ligands with their types. So let's start. Complexometric Titration. Complexometric titration is a type of volumetric analysis used in chemistry to determine the concentration of metal ions in a solution by forming a stable complex with a chelating agent, which is a chemical compound capable of binding to the metal ions. The endpoint of the titration is reached when all the metal ions have formed complexes and are no longer free in the solution. Here's an example. Let's say you want to determine the concentration of calcium ions, Ca2+, in a water sample. You would use a chelating agent called ethylenediaminetetraacetic acid, EDTA, as the titrant. EDTA can form a complex with calcium ions, and the reaction is as follows. Ca2 plus EDTA to give Ca, EDTA complex. Next, to perform the titration, first, add a known amount of EDTA solution to the water sample containing the calcium ions. Second, slowly titrate by adding the EDTA solution until the endpoint is reached. At the endpoint, the solution will change color due to the formation of the calcium EDTA complex. You can use a color indicator to help detect this change. Third, record the volume of EDTA solution required to reach the endpoint. Fourth, use stoichiometry to calculate the concentration of calcium ions in the sample based on the volume of EDTA solution used and the known concentration of the EDTA solution. Complexometric titrations are widely used in analytical chemistry for the determination of various metal ions in solution. The choice of chelating agent and indicator depends on the specific metal ion being analyzed. Types of Complexometric titration. Complexometric titrations involve the titration of metal ions with a chelating agent, complexing agent, to determine their concentration. There are several types of complexometric titrations, each tailored to analyze specific metal ions. Here are some common types. First, direct titration. In a direct complexometric titration, a known volume of the metal ion solution is titrated directly with the chelating agent. The endpoint is reached when all the metal ions have formed complexes with the chelating agent. Example, determination of calcium ions, Ca2+, in a water sample using ethylenediaminetetraacetic acid, EDTA, as the chelating agent. Second, back titration. Back titration is used when the metal ion reacts slowly or incompletely with the chelating agent. Instead of titrating the metal ion directly, you add an excess of the chelating agent to the sample and then titrate the excess unreacted chelating agent with a standard solution of another metal ion. The amount of the standard solution required to reach the endpoint is used to calculate the concentration of the original metal ion. Example, determination of the concentration of hydrochloric acid, HCl, in a solution by titrating it with a sodium hydroxide, NaOH, solution, and then back titrating the excess NO with a hydrochloric acid solution. Third, masking and demasking. In some cases, there may be interfering ions that can also form complexes with the chelating agent. Masking agents are added to complex with interfering ions, preventing them from reacting with the chelating agent. Later, a demasking agent is added to release the original metal ion, which is then titrated. Example, analysis of aluminum ions, Al3+, in the presence of interfering ion ions, Fa3+. Sodium citrate can be used as a masking agent for ion ions, and then a demasking agent like hydrochloric acid is used to release and titrate the aluminum ions. Fourth, selective titration. Selective complexometric titration is used to determine the concentration of a specific metal ion in a mixture containing other metal ions. Specific chelating agents are chosen to form complexes only with the target metal ion, allowing for selective analysis. Example, determination of lead ions, Pb2+, in a mixture containing various metal ions using dimethylglyoxime as a chelating agent, which selectively forms a complex with lead ions. Fifth, sequential titration. In a sequential complexometric titration, different metal ions are titrated one after the other using specific chelating agents. This is often used when there are multiple metal ions present in a sample, and you want to determine their concentrations individually. Example, analysis of a mixture containing calcium ions, Ca2+, and magnesium ions, Mg2+. First, calcium ions are titrated using EDTA. Then, magnesium ions are titrated separately using EDTA. 6th, ethylenediaminetetraacetic acid, EDTA, titration. EDTA is a common chelating agent used for complexometric titrations. It can form complexes with a wide range of metal ions. EDTA titrations are versatile and can be used for various metals. Example, determination of the hardness of water by titrating calcium and magnesium ions in the water sample with a standardized EDTA solution. 7th, crown ether titration. Crown ethers are cyclic polyethers that can selectively complex with specific metal ions. They are used in selective complexometric titrations for metals like potassium, sodium, and ammonium. Example, determination of sodium ions, Na+, in a sample using a crown ether such as 18 crown 6, which forms complexes selectively with sodium ions. Note: the choice of the specific complexometric titration method depends on the nature of the metal ions being analyzed, their reactivity, and the presence of interfering ions. The selection of the appropriate chelating agent and titration conditions is crucial to obtaining accurate results in complexometric titrations. Ligands. Ligands are molecules, ions, or atoms that can donate electron pairs to form a coordination bond with a central metal ion or atom. These ligands surround the central metal, creating a complex or coordination compound. Ligands play a crucial role in stabilizing and determining the properties of these complexes in coordination chemistry. They can be classified into different types based on the number of electron pairs they donate and their charge. Common examples of ligands include water, H2O, ammonia, NH3, chloride ions, Cl, and organic compounds like ethylenediamine, An. Ligands can be classified into several categories based on various criteria, including the number of electron pairs they can donate and their charge. Here are some common classifications of ligands with examples. First, monodentate ligands. These ligands can donate a single pair of electrons to the central metal ion. Example, chloride ion, Cl, in CuCl2 H2O, 4, where Cl acts as a monodentate ligand. Second, bidentate ligands. Bidentate ligands can donate two pairs of electrons to the central metal ion, forming two coordination bonds. Example, ethylenediamine, An, in Cu(N2, 2+, where each N molecule forms two bonds with the central copper ion. Third, tridentate ligands. Tridentate ligands can donate three pairs of electrons to the central metal ion, typically through three donor atoms. Example, triethylenetetramine, TATA, in Fa(TATA, 3+, where TATA binds to ion through three nitrogen atoms. Fourth, tetradentate ligands. These ligands can donate four pairs of electrons to the central metal ion. Example, EDTA, ethylenediaminetetraacetic acid, in Cu, EDTA, 2, where EDTA forms four bonds with the copper ion. Fifth, polydentate ligands, chelating ligands. Polydentate ligands have multiple donor atoms and can form multiple coordination bonds with the central metal ion. Example, EDTA is also a polydentate ligand because it can form multiple bonds with a metal ion. Sixth, ambidentate ligands. Ambidentate ligands are capable of donating electron pairs from two different atoms but can only form one coordination bond at a time. Example, nitrite ion, NO2, can bind to a metal ion through either the nitrogen or oxygen atom, but not both simultaneously. Seventh, anionic ligands. These ligands carry a negative charge and donate electron pairs to the central metal ion. Example, sulfate ion, SO42, in Mg, H2O 6, SO4, where SO42 serves as an anionic ligand. 8th, cationic ligands. Cationic ligands are positively charged and can form coordination bonds with metal ions. Example, ammonium ion, NH4+, in Pt, NH3, 4, Cl2, where NH4+ acts as a cationic ligand. Note: these classifications help describe the coordination chemistry of ligands and provide insight into their bonding characteristics and the structures of coordination complexes they form with central metal ions. The choice of ligands can significantly affect the properties and reactivity of coordination compounds. Thanks for watching this video. If this was helpful, then please kindly do a subscribe to our channel. Thank you.